Hello, everyone. So we're going to wait a few minutes for everyone to join. And while we're waiting, maybe you can tell us where you're coming from. Today, I'm with H.E.A.R.T Watanabe and Victor Paléologue. We're in Paris at Southern Robotics Europe. So we'll be starting in a few minutes. So for those who just arrived, I was saying that we're going to wait a few minutes before everyone joins. And today we're going to be talking about planning for real human-robot interaction. If some of the participants are working in robotics, it would be nice to know. You can use the chat to tell us what robots you're using or which application you've seen robots being used in real-world scenarios, since it's today's topic. So yeah, really don't hesitate to use the chat to share with the other participants and with the panelists. And also we're going to be using the chat to answer to your questions at the end of the presentation. Still 2 minutes and then we can go. So we have Dave from London and he's using Now. Hi, David, and thanks for being with us today. So people working with Now and Pepper in different projects. Different versions also with Now Robot. Nice. There's many people from London. Germany. Somebody working with the H.E.A.R.T project. Great, so I think we can start now. So good afternoon, everyone. Thanks for being with us today. We're going to be talking about planning for human interaction in real-world scenarios. So today I have Victor Paléologue and H.E.A.R.T Watanabe here with me. So they're both engineers from our team, software team at Southern Robotics Europe. So today's talk is going to be composed of 3 parts. First, Victor is going to introduce the basics of symbolic planning and explain how it can be used in human-robot interaction. Then H.E.A.R.T is going to present us an application It's going to illustrate how we can use this symbolic planning with one example on paper. And then Victor is going to dive into the details of how we can bridge the gap between this planning module and the actual robot behaviors. So we're going to see a video with an explanation of a real case scenario that we use here at Southern Robotics. So as usual, this presentation is going to be recorded, and then you can use it and watch it later. It's going to be on our YouTube channel in a few days. And yeah, as I mentioned before, don't hesitate to ask your questions on the chat, because we're going to have first the presentation, and then you'll be able to ask your questions to Victor and H.E.A.R.T. So yeah, don't hesitate to ask your questions to the chat. So let's go back to our speakers. Victor has been a software engineer here at Southern Robotics Europe for almost 11 years, and he recently graduated with a PhD at Sorbonne University, demonstrating that users at home can teach new behaviors of robots using the spoken language. His work ranged from developing tools and SDKs to help users becoming wizards of robotics to making robots' cognitive systems more powerful. So thanks, Victor, for being here with us today.
Thanks.
H.E.A.R.T is also a software engineer at Southern Robotics Europe. He completed his master's thesis in robotics in 2018 at ETH Zurich, during which he implemented a visual kite tracking system for application in airborne wind energy generation. At Southern Robotics Europe, he has been working on the autonomous capabilities of Pepper, notably on the design of exploratory behavior through interaction with the environment. And H.E.A.R.T, thanks for being here today.
Thank you.
So now that we introduced our speakers, I'll give the floor to Victor and H.E.A.R.T, and I'll come back for the questions later.
Thanks, Susanna. So I will share my screen for
Yes.
up. I hope we're fine. So, welcome everyone. I'm really happy to see you all joining today for this webinar. I'm going to talk to you about the planning algorithms, this technique, and how we used it for human-robot interaction in the real world, actually. So it's a bit of a fresh touch on decision-making. You will see what we used to do and how planning changes the game a little bit. So all this work, our work stems from the general question of what a robot should do and how to code it. For instance, a robot can be around and explore its surroundings. And we expect that if a human goes to meet the robot should react and greet you in a pleasant way. So there is this idea behind the behavior of the robot, that the robot has its own life. I like how Cynthia Brezial presents that. She says that it's likely that an owner would encounter his or her robot on a daily basis, either by intentionally seeking it out by chance as the robot goes about performing its chores, or perhaps initiated by the robot seeking out the person. So in that image where we really live along with robots, it's a bit still futuristic today, we expect the robot to have their own existence, their own life, and maybe their own character. And we expect them to be aware, looking around, checking for interaction with us, being always open for interaction. And you know, Pepper and Now, they were designed to be a bit joyful, childish, clumsy, because the purpose there is also to share good times and not just be a service robot. There are other robots like that, you know, for instance, Aibo was totally about this. Vector also is for entertainment, you know, and the Spoon AI's Creatures is a new avatar-based character that starts being seen in Paris. In practice, but we know in practice the robot also have a very specific business purpose, and all of that together, all these behaviors, they should be able to mix together. So we expect actually quite complex behaviors of robots in general. So let's talk about how we did that so long before I jump into the planning solutions. In Pepper and in Nao, we have the solitary and interactive modes. The idea is that there is a zone around the robot where if you go in that zone, the robot should interact with you. And if you're away, the robot can lead on interactive activities. So what I mean by activity is just a piece of application coding the behavior. It can be a choreographed behavior, it can be an Android application, it can be any piece of code that we decide to run on the robot that changes the behavior of the robot. With choreograph, we have distinguished the interactive activities and solitary activities. And with the autonomous life of the robot, we had a rule that if you are in the interaction zone, the interactive activities will take precedence and override the solitary activities. So this should produce, the behavior that I showed you in the GIF before, where the robot goes to talk to you instead of keep on doing what it was doing before. So that works fine, but it's a bit limited by the fact that if we really want to reuse the activities from the community, if several developers produced different activities, interactive or not, actually it's hard to mix them together and build a complex behavior, as I told you. So to do that, we need a way to select the behaviors. So the first idea that we proposed was to have trigger sentences. So these are basic things in our framework, where we have a basic channel and we can extend, it provides a dialogue, and we can extend the dialogue with trigger sentences. For instance, dance Gangnam Style, and the robot should start his Gangnam Style dance. Or what time is it, etc. We can extend actually the way we want. But this is just user interface to help the user select what the robot wants to do. It's not really the robot deciding to do things among many things to do. To go in that direction, we also introduced the launch trigger conditions. So the start of the activities could be programmed thanks to these conditions. If this condition is true, the activity should be selected and started. So we have a sample, for instance, in the documentation where we show for a robot Pepper waving to attract people. The rule here says that if the waving activity was not run for 60 seconds and there is at least one person in zone 2 for 10 seconds, start the activity. That's straightforward, actually, that works. But if you mix several behaviors together, you are going to have to tweak the conditions on each activity to tune the overall behavior. Like you really, you get into invasive changes in every activity to tune the mix and the selection of behaviors, actually. And this is because it's the programming is strict. Here we write exactly what we want in which conditions. And if we add the new behaviors together, there is no room for decision making. You have to rewrite differently the code. You have to update the code all the time. And there is no adaptation possible in these conditions. A different point of view of this problem is also that you have no distinction between what can be done and what should be done. If you want to have decision making, you need some room where things can be done, but they are not necessarily done. You need the trigger to be an independent decision from the feasibility. Right. So we're going to show a bit more advanced models and introduce the planning and how we can solve this. Often when we think about AI, we think about very complex stuff, but it's really just programming. In the end, this is all programming. It's a lot of ifs. Typically, behavior trees can really help scale code for video game AI. It's really a good approach to make large-scale behaviors in general. And state machines also, they can help, and Petri networks, they can help doing that. They are more advanced models than just programming, but in those cases, they are still strict programming. But we also have planning problems that I got interested into during my thesis. Planning problems and Markov decision processes that are kind of alike. Markov decision processes are a bit of generalization on planning problems. I'm going to go a bit in the details here. So as I told you, the behavior trees and state machines, they are strict. It's like the trigger conditions. You have to hard code exactly in which conditions which action should be run. Whereas with planning problem, because we distinguish feasibility and trigger, we define the actions on one side and while running them on the other side. It's not strict, and it's easier to change the behavior if it's programmed with a planning problem, at least in theory. In Markov decision processes too, and it's even better because there are algorithms suited for adaptation, and we have seen examples where you can actually have learning on top of that. So these models are interesting, and we got into the planning problems, planning models, because it had a lot of advantages. Before I show you the advantages, I'm going to tell you a bit more what is a planning problem. So instead of writing the code directly where you say, if this condition is true, do this, do that, then that, you're going to write a goal. So you are going to have to define a state, a final state you want to reach, and a set of actions. And the planner will figure out the plan, so the set of actions to perform to reach that goal. So this is where you have this little freedom of decision making open and allowing a bit more complex behavior to emerge. So the advantage of these approaches, first, it's really to solve problems when the combinatorics are too high. For example, motion planning is a very good example. Really, there are too many points in space, so we need the planning algorithm because we cannot program everything in detail. But I think the same things apply to complex behaviors in H.E.A.R.T. Also, the planning problems have the advantage of looking ahead, so really looking at the problem altogether. It avoids getting stuck in local minima, tries to figure out efficient solutions. So it's actually efficient in terms of the result. The result is usually a good one. You can really control that. And the semantics are powerful. So here I'm talking also about the symbolic planning, where you can actually use logics to constrain a problem. But the idea is that because you're talking about restrictions, you don't really constrain what robot should do. You really constrain the space of what's possible. There's still a piece of freedom. So there are more reactions possible. You don't restrict the reactions that are possible for the robot. In symbolic planning, because it's using logics, it's better for understandability and explainability. If there is a complex decision there, theoretically, we have the tools to understand why it was done like that, why it's optimal, etc. Also, the states I'm talking about, so the final state, initial state, there are inputs to the planner. So the planner don't depend on the state directly. It's just an input for the algorithm. So it's more scalable in terms of software. You can cache results. You can do many things like put it on the cloud using an AWS Lambda. It's actually more powerful for scalability in terms of practical programming. So for me, I represent this in a simple manner, just with that diagram. I have some state that goes into the planner, and the planner outputs a plan. I see other advantages, more related to H.E.A.R.T, is, as I told you, the same problem, the same domain in a planning problem can actually encode a large variety of behaviors. Like depending on the state and depending on the goals, you have many different sequences of actions that can be produced automatically. So it scales up better if you really get into high combinatorics. It also helps a bit in the programming, the way we program with a planning system, with a planner. It avoids us to deal with the fallback logics. You know, if you get into that little trap there, you have to have a special behavior. Normally, you can really encode that in the problem, and you really don't have to do those fallback management all the time. I'm going to give you an example about that. And also, it invites, because of the way it's architectured, it invites us to write the behaviors as atomic reusable actions. It actually helps in coding a large behaviors in terms of software engineering. So let's see an example. We have a robot serving dishes. The robot is next to a table. Someone bumps into it. Now the robot is too far from the table and it's rotated. So now the new situation, the robot is not close to the table anymore, is incompatible with serving dishes, because serving dishes has a precondition is to be next to a table. So the task is immediately stopped. The goal to serve dishes now is still unsatisfied, but the situation changes, and the planner determines with this new state, determines that we have to navigate back to the table to serve the dishes. So the robot just go back to the table before it's able to serve dishes. So just because we coded the way, we coded the fact that the robot should go to a table to serve the dishes, intrinsically makes the fallback logic automatically, because if for any reason the robot is moved away, it knows it has to go back to the table if it wants to serve dishes. So that's really practical when you were programming tasks like that. Okay, so I wanted to talk a bit about exactly what symbolic planning is and how we can go further. There's a language called PDDL for symbolic planning, and it supports domain-independent solvers. It means you don't have to train anything. You can just solve a PDL problem right away, and the decisions based on logic are explainable. But there is a limitation, a big one. It's that it requires a fully observable world. But you know the world is not fully observable. The real world isn't. And this is why we have more extended, there are more extended models like partially observable MDPs that are really known because they were used in StarCraft and they were used in AlphaGo. They can really solve, an AI using a POMDP can really solve very complex problems and produce very complex behaviors. And it would be more suitable for the real world, really. But it requires a lot of training, and it's not inherently explainable. So if we try to apply it on a social robot, we're going to be limited. We can see that in research papers, it works, but since there is no generalistic solver, they always have to train the robot on the task, and the robot can only do that task. The data must be realistic, so if you want to train it, you actually have to do a lot of real interaction, and to do that, maybe you really need the robot to behave the way you want, so you can use what we call a wizard of Oz. You know, somebody is faking the intelligence of the robot. It's a human intelligence behind the robot. But it means 1,000 of hours of interaction with somebody behind the robot that is actually faking the intelligence we expect. And we also need annotation afterwards. So because of that, that's a lot of work. We just think we can automate this work. We can just write the program. And usually the POMDP solution is just too far away to, needs too much work to use it. So what we can do is actually using PDDL, for instance, to write a behavior, or anyway, And since the model resembles, gather data from the real interaction we've implemented with PDDL, gather data, state action data, that is exactly what the POMDP will need for training later. So it's actually a good intermediary step that doesn't just replace POMDP forever. It's a good start, even if it's imperfect. And later on, as we gather data, we can actually use POMDP and train a POMDP to replace the PDDL solution, to go into the finer grain details that the PDDL won't be able to solve. Okay, that's all for me. I'm giving the floor to Shin, who's going to tell you about real-world application.
Thank you, Victor. So now we will work through a simple H.E.A.R.T problem to really get a feel for the power of planning approaches, and in the process, hopefully learn a little bit about the syntax of PDDL. So we have a scenario. We have a situation, which is that there are unhappy people in this world, unfortunately. And then the goal is to make them happy. Pepper can find them, greet them, and also tell them jokes, and hopefully they'll end up happy. So if we were to do this the traditional way, it would look something like this in pseudocode on the left. So we first check if there's a human around. If there isn't, we find them. Then we check if they're greeted. If they're not greeted, we greet them. And then finally, we joke with them. So this looks simple enough, but what if we want to change the behavior on the fly? In other words, what if we want to choose dynamically whether to greet them or to make people happy, or both? So this is what the result would look like. So here we added two parameters, should greet and should make happy, which toggles the actions greet and joke with respectively. But also notice how in the first line, we had to add some code to figure out whether we had to find a human. So in this case, if either we want to make happy, we might want to make users happy or greet them is true, then we also have to find human. So as this example shows, as the number of goals that we want to achieve grows, the added logic also grows exponentially. So this approach is not scalable for applications that require complex behaviors. So now we are going to take the same problem and solve it using PDDL. For this, I will share my screen with here. So hopefully you can see my Android emulator. Great, showing an application that we've developed where we can write PDDL problems with a user interface and solve them. And the way it's solved is we use a planner, off-the-shelf planner called Fast Downward, which has been ported to Android by Victor. So here I've filled in all the problem already, but we'll go through it together. So PDDL has two main components. One of them is the domain. So the domain describes the universal aspects of the problems, so things that don't change or with different problem instances. So the domain has 4 subcomponents: types, constants, predicates, and actions. Types are simply the types of things that exist in the world. So here we have humans and emotions. Constants are things that stay the same, that are always present, regardless of each instance of the problem. And so here I put 3 types of emotions that are always going to be around. So happy, neutral, sad. Predicates describe the state of things in the world or relations between them. Here I have feels, which is a predicate that takes human and emotion as a parameter. This predicate describes the relationship between a human and an emotion. So a human feels an emotion. We can have predicates with one parameter, like a human being around, describing the state of the human, or also a human is greeted. Here, so the fourth subcomponent is actions. Actions describe a change in the world and is described using predicates. So actions have three sections. One is the parameter, which defines the type of things that we perform an action on. So looking at the first action here, we have joke with. We're joking with a human, so the parameter is human. Second section is a precondition, and this is the state of the world that need to be satisfied in order for this action to be called. So that doesn't mean that the action will be called, it's just that it's available. It's what Victor talked about before about feasibility and trigger. And for the third section is the effect, and this is what the action results in, and also using predicates or a combination of predicates. Here we have joke with, in which we need a human to be around, and results in the human being happy. We have a greet action, which also requires a human to be around and results in the human being greeted. And finally, we have find human, in which we have no preconditions, and we have as an effect that the human is around. We have here problem is the second component of PDDL problems. And this describes the specific situations that we want to solve. So it's composed of objects, initial states, and goals. Objects are simply the things that exist at for this problem. Here we have 4 humans, Alice, Bob, Charles, and someone. Initial state describes the state of the world at the start of the problem. And so here we have Charles, which is around, who's around, Alice, who feels neutral, and Bob feels sad. For initial state, we don't have to put things that are not true, because the planner assumes that everything that's not written is not true. So I didn't write Alice is around, for example, so Alice is not assumed to not be around. Goals is a counterpart of initial state. It's how we want the world to look like at the end of the plan. And here we can have goals that are like initial states as one predicate, or we can have complex goals also. But what's important for goals is that we do have to specify things that we don't want to be true. Otherwise, the planner considers it unimportant. So the first goal says that for all humans that exist, so the 4 humans above, if they are around, then they must feel happy. The second is very similar. For all humans, if they are around, they must be greeted. And for the third one, it's a little more complicated. If there is no human around, then we have to make sure that there is a human around. Okay, so let's solve this problem using a planner. Here we click on the plan and it talks to the planner service, which is another application. And let's see what we get. Plan is successful. And we get greet Charles and then joke with him. So this makes sense because in the initial state, we had put that Charles is around, and one of the goals was to greet him and the other was to make him happy, which we can do with joke with. What would happen if we change, for example, the initial state? We just uncheck Charles is around. There's no one around. So now we get find human, Alice, greet Alice and joke with Alice. So if we look at the initial state, no one is around. And one of the goals is that if no one's around, we have to make sure that someone is. So the planner gets the first human that's around, finds them, and then satisfies the other two goals. Let's now change the goal. Let's uncheck the greeting goal and see what the planner gives. Great, so it's the same plan except we don't have to greet, right? So it's just find Alice and joke with. So I hope it was clear here that compared to the traditional approach, the PDDL relieves the programmer from the burden of adding code and logic for every change in the goal or the initial state. And if you want to if you want to play around with PDDL, both of the apps I mentioned are open source, and we'll have a link in the chat. So please download it and play around with it on your own. So now I will go back to the presentation. Great. So now that we've seen a toy problem, let's go to the real world. So we have, over the last year, we have been developing an application that integrates the planner in to make Pepper a receptionist robot for the office here in Paris. So I will describe briefly the flow of the application here. So I start with the diagram shown by Victor before. Every time there's a change in the state of the world, the planner is called and outputs a plan. The plan has a sequence of actions which need to be converted to real actions using the H.E.A.R.T SDK, which interfaces with the robot actuators and brings about change in the world. These actions can directly update the state of the world, in which would relaunch the planner. Regardless of these actions, though, the world changes constantly. So we have the sensors on the robot, which grabs data, and we have what's called extractors that process the sensor data and converts it into meaningful states that for the planner. And then the state is updated, and then the loop continues. So for implementing this architecture, we first had to define the possible states that are relevant for the task of receptionist, as well as the goal that the robot wants to achieve. Once we defined these, we had to build actions using the H.E.A.R.T SDK to yield the desired state changes, and conversely, implement extractors, again using the SDK, to recover the state changes that we want to, that are relevant for the task. Finally, we implemented an engine that reruns the planner every time there is a change in the state of the world. So let's see it in action. We have a video here of the receptionist robot. Let's see if it plays. Okay, sorry, a little technical issue. Great. So hopefully you can hear the sound. Great. So in the beginning, the robot, there's no human around. So the plan which you can see at the top right, is empty. So the robot is idling. As soon as the robot sees a human, it outputs a plan. The plan is run and outputs a plan of 4 actions, which is to engage the human, show the welcoming menu, identify the human, and to say goodbye.
Bonjour, en quoi puis-je vous aider?
Je suis un employé.
Here it shows the welcoming menu.
Vous travaillez. D'accord. Vous pouvez scanner le QR code d'invitation ou me dire votre nom.
Here it tries to identify the human.
Victor Paléologue.
Est-ce bien vous?
Oui, c'est moi.
Très bien.
Oops. Oh no. Sorry. Technical issues. I think I was. And
Oui, c'est moi.
Très bien.
here, notice that the plan changed completely because now we have more information about the user. This is a case of non-determinism because the identify user action outputs a different state change depending on the profile of the user. So our planner deals with this issue by replanning. So now the new plan is to ask the user if he wants to check out, then check him out, and then to say goodbye.
Souhaitez-vous enregistrer votre départ?
Oui. Oui.
Ok. Votre départ est enregistré. Bon après-midi.
So I hope you were satisfied with real world use case of what we've been talking about for the last 40 minutes. And I'll pass the floor over to Victor.
Okay, thanks. Okay, I'm wrapping it up. So today we've seen how we use the planning for human-robot interaction in the real world. And we've seen that actually it's usable. It is possible to use planning for H.E.A.R.T. It is also Shin, can you change the slide? It's more flexible and scalable, actually. Helps getting in more complex behaviors. Also, it paves the way on more intelligent algorithms like POMDP and allows us to gather data for future learning and adaptation. All that work we've done around this subject are available online on GitHub, actually. There is a library, a wrapping library to use PDL planners in general that is independent with a very open license. Fast Download Android, which is GPL and is available for Android, but you can run it as a separate service. And the PDL Playground, Shin's app, if you want to try out PDL yourself with some helper and with some tutorials around. That's all for me. Thank you.
Thanks a lot to Victor and Shin. It's really cool to see this paper at the reception that we've been having here for 1 year and to explain it to the whole world and also to give all these tools available so that people can play around. So yeah, I just gave you to everyone this GitHub repo. So as Victor was explaining, you can use it. It's open source and you can play with it. And now we're gonna pass to the Q&A session. So if somebody has questions, please you can use the chat. We're gonna give a few minutes to have a few questions. Okay, so there's this first question. Does this plan consider things like proxemics?
Yes, so it's encoded in the extractor. The extractor is actually quite intelligent. You know, it's actually a challenging piece of information to know that there is a human around that is engaging you. So we're using the whole stack of Pepper, you know. There is an API that tells you when humans are around, that tells you their distance, and we can check that they are in a zone that is interesting for us, and they are also sorted, and there is a recommendation in the key SDK that tells which human is the most suitable for engagement. So we're using the key SDK for that, and so it's based on proxemics, yes.
Okay.
But it doesn't appear directly in the plan. As you can see in the plan, it's logics, it's symbols. So at this stage, we have no numerical quantity, you know, it's qualitative and not quantitative. So not everything can be expressed directly into a state. So we have to do it with intermediate symbols that we define ourselves.
Thanks, Victor. There's also one question about publication describing these works. Maybe in your thesis, it's already a part of it.
Yes, yeah, my thesis in 2019 was already using this. So we were using PDDL in the system. It was actually more focused on the dialogue part. So we even had the dialogue mechanism, like replying to the user who's talking to you. Rules like that are encoded. So I should maybe find a link for you and put it in the chat. That'd be interesting. It's used there, but it's also used with several applications. H.E.A.R.T participated there also by making exploration behaviors. And those behaviors were autonomous, and the robot wanted to go explore at the same time that the robot wanted to meet people and ask them things. And it goes actually beyond with a conflict management system to make sure even conflicting drives, conflicting goals like that can work together.
Thanks for that answer. There are still coming questions. How does your system deal with non-deterministic environments? If so, how do you encode the probability of an action to happen?
So this way, this system here, it's quite simplistic. For instance, the identification, it will suppose a positive answer. Let's say it will suppose something. The planner will see the action. The action will pretend to have a result. So we define what is, let's say, the normal result. And if a different result is output, it's not a problem. The planner will restart and figure out something new. So actually, it's dealt with by the fact that it's always replanning every time the state changes. So if something non-deterministic happens, it will react a posteriori. So maybe there's a slight moment, you know, 100 milliseconds or so or less, where the robot might take the wrong decision, but it's so short that in general you don't feel it.
Okay, there's a related question about Victor. You mentioned that planning allows to avoid local optimization, but is it formally proved that planning allows to reach global optimization to reach its final goal? I think it's a bit related to what you just said.
Yeah. So there are optimal planners. Depending on your planner algorithm, you can have guarantees, and obviously the optimal planners, to be sure that they are optimal, they really have to go through the state space quite exhaustively. So the planning can be quite long. So if you want performance, you will maybe as a trade-off get rid of optimality. So you will find what's the best estimate that the planner finds in that case. So it's not necessarily optimal, but you can have that strong guarantee if you want. But usually I think we don't really need it.
Okay, and maybe a bit related to that, as a complement, why did you choose the planning that we were using for this particular application on paper? Maybe talking a bit through this.
Why did I choose what?
The planner, like in when you were choosing the planning, how can you maybe give an idea of?
So fast downward is quite known. It's not the top-notch, the best, whatever, but it's well known. There's a bunch of tools around. There is a community also. So we felt more confident of having something reliable there. And also it was using CMake for the building, so it was easier to port on Android, and it gave us sufficient large variety of planners to tune the planning algorithms we wanted. So yeah, we use that one because of that. But we know there are other planners out there, and if we have to redo it and improve it, I think there are more lightweight planners, more modern ones, and more powerful ones also, because we're only using a small set of PDDL features. We can actually go further, even go into probabilistic things, you know, just like the other question, we can actually go much further. And for me, it's more like let's say a first shot with some simplifications there.
Thank you. And Angelica Lim has another question. She said, I might have missed this in the beginning, but can you compare or contrast this behavior planning with motion path planning? Is it fundamentally similar, or what are the important differences between both?
So it's actually similar. For Angelica, I think I can find back a source that defines exactly what planning is. There is a shared model, mathematical model that is really common between motion planning and symbolic planning. And yes, it's just that in motion planning, the techniques are very different because the 2D space or 3D space behaves much differently than the logical space. So that's why there is a difference, but it's the same theory behind.
Perfect. Okay, I'll just continue go through the question. As humans are very hard to model, how could planning work in social interaction where post-conditions are near impossible to know? For example, making someone happy can be a really hard task, of course.
Yes, exactly. Yeah, I expected that. I think it's really important to remember that. It's not all magic. We cannot predict that future. We still have to stay humble there. It's really about the intent of the action. Like an action is targeting an effect. Every action the robot does has a potential effect, and the goal is to reach a certain state. So the planner will select something that it's defined as having that effect. But if you don't have the feedback where you check that the effect is really made, you are never sure, actually. So there are many simplifications in what we have done here. Sometimes we consider some, for instance, the greetings. I don't know, we don't check that the human really heard or replied back or something. So maybe you said hello, but the human didn't really hear and didn't feel greeted as a result. So that's a very legit question. And to improve this, you really need the actions to have that feedback there, have that checking, double checking that the effect is really there. Well, it's actually, I think it's very good research topic to actually take a system like that already supposes things and try to learn and try to double check and verify that the actions are really doing the effect we want. With such a system, you can actually have actions, robot that figures out how to make action best to really have the end effect.
Yeah, and if I can talk a bit also about it, I think, of course, when we are talking about emotions and saying that the goal is to make someone happy, it doesn't mean the same for one person to the other one. Of course, on that part is non-deterministic and it's very hard to know the effect we're having. But as Victor is saying, also if we take back all this usage of social robotics in real case scenarios and the uses we have today, actually the goals are maybe more realistic and less based on perception capabilities of the robot, like being sure that somebody's happy or not, or just detecting a smile. For example, in the case of paper receptionists, the goal is to check in an employee or a visitor. And this, we can in fact know if it's the case. So I think one good point also will be, while using this in real case scenarios, is to really don't forget what the real goal is or the real task is for your robot. And maybe this will also simplify the way you're using it. Okay, so Angelica wants to rebound a bit on the optimality. So is optimality in H.E.A.R.T even defined? Is fastest or shortest always best? What does optimality mean in H.E.A.R.T for you?
Here, really, in practice, we had the smaller number of actions. That's really not a great measure. So we just optimize the fact that the robot will go straight to the point with a fewer number of actions. But there is a system of cost also. You can add cost to different actions and maybe have a preferred action that are have a smaller cost, or longer action have a higher cost. And at some point you may want to add the time. Maybe let's say if you want to also go to one place or another, in that case you also want to have some cost there. And it gets a bit complicated, you know. You cannot put everything on one metric actually for the cost, and this is where the extended models become more interesting. Let's say with an MDP or a POMDP, you can have different sources of reinforcement, and let's figure out the weights, you know, like with deep reinforcement learning, figure out the weights of each constraint by itself. That would be the best. So again, here it's very simplistic and just the number of actions, and it would be relevant. Number of actions, let's say if you have a it would be relevant for, let's say, exchanging a message to a human. Not being, it's not super nice to see it that way, but you could say, what is the shortest path in terms of information to give to the human to give them the whole set of information? You'll figure out the few sentences and the few screens that give the most information and gets the fastest to the point. That would be legit in some cases, I guess. So it's not completely crazy, just.
Yeah, there's understood that say that maybe rather than optimality, it could be simply guaranteeing the visibility. Can the goal actually be achieved at all? I think that there's a good point in there.
Yes, sure. So that's what the planner does. It says if the goal cannot be reached, there is no solution to the plan. It's actually maybe one of the problems that there is no solution to the plan. It's you have to dig into explainability, to go into the details and have to figure out why it's not possible.
And yeah, one more question that you were already answering a bit. Could deep learning approaches for intent recognition or emotion recognition or something similar can be incorporated into this framework? For example, using the predictions of confidence.
So I imagine that depending on what you want to optimize, yes, I can imagine, let's say, maybe you can change an action and have actually your action be intelligent and use a deep learning mechanism inside to make sure the effect is the one we want. You can, let's say, you know that an action should have this effect, and let's say you have an algorithm to see that effect, to double check that effect. If you have that effect, if you can recognize that effect, then you can actually try this action until you've done that effect and maybe learn to do it more efficiently. So I see places where just in the framework, just replacing an action properly inside an action, you can actually put deep learning in there and actually have an action that trains over time.
Cool. Thanks a lot, Victor, for all of those answers. I think we get plenty questions there, but I wanted to ask you, maybe both of you, one more question before we wrap it up. What about the challenges of implementing all this in very short time, and of the last work that you were doing with your team and with other teams at SoftBank? What are the challenges when we're trying to? You already talked a bit about the decision you made about the planner that you used, but maybe are there other challenges of the implementation that you would like to share?
H.E.A.R.T, maybe you want some inspiration there?
Yeah, sure. The challenge, I think, was to have this really nice big architecture and to try to build it incrementally, test it, change the architecture, because sometimes it necessitates defining the ontology, for example, the space of states. If we change that, it can have many impacts on many places in the code. For example, we might have to change the extractor or the actions, and making sure that in each step of the project we have a coherent kind of architecture that works was a very interesting challenge.
And I kind of liked the problems of also optimization and making sure all the events don't come in the right order. If you have all these events coming at the same time and you have to replan all the time and figure out when to replan, this little piece of engine is actually a bit of a challenge. So I wrote it several times in my thesis and here in C++, in Kotlin several times. And it's always a bit of a challenge to make something smooth that can replan in a fluid manner.
Perfect. So thanks again, Victor and H.E.A.R.T, and thanks for all the attendees today. So today was our last webinar before the summer break. We're very happy to have presented this work that was done at SoftBank in the last year. And again, don't hesitate to go and check the repos when you can have the code and try it out yourselves. And of course, if you have further questions, also while using the PDDL approaches that we presented, you can also contact H.E.A.R.T, Victor, or the H.E.A.R.T team directly. So yeah, don't hesitate, and thanks everyone for being here today.
Thank you,
Victor and H.E.A.R.T, you have many compliments on the chat.
Thank you, everyone.